Hello everyone. Today we are going to explore an important topic in the world of technology, that is why software engineering matters today. Before we dive into software engineering, let's quickly look at what we will cover in this video. First, we will start with what software engineering actually is and why it exists. Understanding the purpose behind it helps us to see why this structured development is so important in modern technology. Next, we will explore why software engineering matters today, especially in the world driven by digital systems, mobile apps, cloud platforms, and AI powered solutions. After that, we will discuss the key pillars of software engineering, that is, the fundamental principles that guide how reliable and scalable software is built. Then, we will walk through software engineering lifecycle, looking at the journey of a software from an initial idea all the way to deployment and maintenance. Once we understand the life cycle, we will move into the core domains of software engineering, which represent the major areas that are involved in building and managing software systems. Following that, I will provide a detailed explanation of each domain so you can clearly understand how each part contributes to the overall development process. And finally, we will look at how software engineering aligns with the DevOps and modern industry practices, showing you how today's organizations deliver software faster, more reliable, and with continuous improvement. So let's get started and begin our journey in the world of software engineering. Software engineering is the engineering principle or discipline for designing, building, testing, deploying, and maintaining the software systems using systematic methods. So it treats software development as engineering, not just coding. Think of civil engineering. When engineers build a bridge, they do not simply start constructing randomly. They follow requirement analysis, they design blueprints, the safety testing, construction phases, the maintenance plans. Software engineering applies the same engineering discipline to building software systems. Instead of bridges and buildings, software engineers build mobile apps, cloud platforms, banking systems, e-commerce systems, and AI-based platforms. The world today runs on software. We have banking systems, healthcare systems, transportation systems, education platforms, even agriculture and manufacturing systems. So modern companies are software-driven companies. Companies like Netflix, Amazon, and Google are essentially software platforms. These systems must scale to millions of users, and they must remain reliable and update frequently, and we expect them to integrate with cloud infrastructure. So this level of complexity cannot be handled with simple programming. It requires software engineering practices. Software engineering is one of the most relevant and impactful careers today. Unlike many fields that focus on theoretical knowledge, software engineering directly contributes to building products that is used by millions of people. It naturally aligns with modern industry practices such as DevOps, cloud computing, agile development, continuous integration and deployment. So this makes software engineering professionals extremely valuable in modern technology organizations. Before we discuss the different domains of software engineering, an important question arises: why do these domains even exist? So the answer lies in the nature of complex software systems. When the software was small, a single programmer could write the entire system. But modern software systems are extremely complex. They involve millions of lines of code, the large development teams, millions of users, and systems running across distributed cloud infrastructure. So because of this complexity, building software requires a different kind of problems at different stages. First, we must understand what the problems we are solving. Then we must design how the system should work. Then we must build the system. Then we must ensure the system works reliably. And finally, we must continuously improve and evolve it. So each of these responsibilities become a specialized domain within software engineering. These domains exist not because universities maybe created them, but because real-world software development demanded them. Here are the core domains of software engineering: requirements engineering, software design and architecture, software construction and development, software quality engineering, and software re-engineering. So together these form what we call the software development lifecycle. Let's understand this through a simple story. Imagine a startup wants to build a ride sharing app. First they must understand the problem. So users want to book the rides easily. Drivers want a system to receive ride requests, and this stage is particularly called requirements engineering. Once the requirements are clear, engineers must design how the system will work. How will the mobile app communicate with the servers? So this is software design and architecture. Next, developers start implementing the system, writing code for mobile apps, the APIs, backend services. So this is software construction and development. When the system must be tested, then the system must be tested thoroughly, ensuring that payments work correctly, location tracking works efficiently and effectively, and the system is secure. So this is where quality engineering plays its role. Once the system is ready, it is deployed on servers and cloud platforms. And finally, over the time, the system evolves and gets improved. So this process is known as software re-engineering and maintenance. Now let's briefly explore why each of these domains is extremely important. First one is software requirements engineering. So the purpose is to understand what the system must achieve. Many large software failures in the history happened not because the developers could not code, but because the requirements were misunderstood. Requirement engineering focuses on understanding what users actually need from the system. For example, imagine a company wants to build a ride-sharing app. So at first glance, someone might say that we just need an app where people can request rides. But once the engineers start exploring deeper, they realize that the system is much more complex. They must identify many requirements, such as maybe the users should be able to request a ride easily, drivers should receive ride notifications instantly, payments should be processed securely, and users should track their ride in real time. So these are all functional requirements, that is the things the system must do. But there are also some non-functional aspects or non-functional requirements that describes how well the system should perform. For example, the system must support thousands of users simultaneously, or the response time should be very fast. The system must be secure, reliable. So requirement engineers work closely with stakeholders, product managers and users to capture these requirements clearly and document them properly. Understanding requirement properly ensures that the development team build the right system, not just build a system correctly. Once the requirements are understood, the next challenge appears. How should the system be structured? Imagine trying to build a large hospital building without a proper architecture plan. It would quickly become chaotic. The same thing happens in software. Large systems may contain many components that may include databases, APIs, the mobile services or applications, the backend services. So without a well-designed architecture, these components become tightly coupled and extremely difficult to maintain. So think of the architecture like the blueprint of a building. Before constructing a building, architects design how many floors it will have, how many rooms are arranged, and how electricity and water systems will be connected. Similarly, architects of software design the structure of a software system. They decide things like how different components of the system will interact, how data will flow between the user interface, servers and databases, how the system will handle millions of users. For example, modern large systems often use microservices architecture. So instead of building one large application, the system is divided into smaller services. Each service handles a specific responsibility. For example, one service handles user accounts, another service handles payments, another service handles notification. So this makes the system easier to scale and maintain. So good software architecture must ensure that the systems are scalable, they are reliable and maintainable. While poor architecture, on the other hand, can make the software extremely difficult to maintain and upgrade. That is why software architecture is considered as one of the most critical skills for experienced software engineers. Then comes software construction and development that transforms the design into a working software. So after designing the system, we finally reached the stage what most people associate with software development, that is building the system. So this is called software construction. At this stage, the developer translates the architecture and design into a working code. But modern software construction is much more than simply writing a code. Developers must follow best practices such as the clean code principles, or the good architecture solid principles, maybe version control systems, code reviews, automated build. So these practices exist because software is built in teams, not individuals. Without proper construction practices, the code base can quickly become very messy and difficult to maintain. So software construction ensures that the code remains organized, maintainable, and understandable. After the software is built, another challenge appears. How do we ensure that the system actually works correctly? Software systems are incredibly complex, so even a small bug can create and cause serious consequences. For example, a bug in a banking system could cause financial losses. A bug in medical system could maybe risk a patient life. This is why software quality engineering exists. It focuses on systematically verifying that the system behaves correctly. So this includes testing individual components, testing the interactions between the system, testing the performance under heavy load. So modern systems or modern companies often use automated testing pipelines where every change you made in a code is automatically tested. So the quality engineering practices ensure that the software remains reliable and trustworthy. Finally, software systems must evolve. Software systems rarely remain the same forever. Over the time, technology change, business needs evolve, and the systems become outdated. For example, many organizations still uses legacy systems that were developed decades ago, and these systems may work but are difficult to maintain and cannot support modern requirements. This is where and why the software re-engineering becomes important. So it focuses on improving and modernizing existing systems without rebuilding everything from the scratch. For example, a company might take a large monolithic system and gradually transform it into a microservices running on cloud platforms. So developers may also refactor the code to improve the maintainability, and it ensures the system continue to remain useful, efficient, and relevant in a rapidly changing technological environment. So this is very important today as many organizations are migrating their systems to cloud infrastructure and modern architectures. Modern software engineering is closely integrated with DevOps practices. So DevOps emphasizes automation, continuous integration, deployment, and collaboration between the development and operations team. This integration enables the organizations to release the software quickly and more reliably. So let's first understand how the traditional software development used to work. In the traditional model, development team and the operation team work separately. Each team had its own responsibilities and goals. The development team or a dev team focused on mainly writing the code. They implement new features, fix bugs, and ensure that the application delivered through the required functionality. On the other hand, operations team or ops team was responsible for deploying the application, managing the infrastructure, managing the servers, monitoring the performance, and making sure that the system stayed reliable in production. While this separation made the responsibilities clear, it also created several challenges. The developers would build the software, but once it was handed over to operations, deployment issues, environment differences, or performance problems could arise. So this gap between the development and operations often lead to delays, communication issues, and slower software delivery. And this is exactly the problem that the modern practices like DevOps aim to solve by bringing the development and operation teams closer together. So DevOps is a cultural and you can say a technical approach that integrates the development and operations team. Instead of working separately, both teams collaborate through the entire software lifecycle. So it also emphasizes automation and continuous delivery to make the software deployment faster and more reliable. This life cycle is often shown as an infinite loop, meaning that the process never truly ends. The feedback from one cycle improves the next cycle. So planning is the stage where the requirements, your goals, features, and tasks are defined. Teams decide what problem the software will solve, what features could be built, and how the work will be delivered, all the timelines and the priorities. So developers, operations engineers, product managers, and stakeholders collaborate here. So commonly used tools in this planning phase are Jira, Trello, Azure, DevOps, and Confluence. Let's consider an example. A company building a food delivery app plans user login system, restaurant browsing, order tracking, and payment integration. So these tasks are broken into user stories like users should be able to search the restaurants, or users should receive order notifications. So this is done in the planning stage. Then the coding stage. Developers write the actual source code based on the plan. So key practices include the version control, code collaboration, branch management, code reviews. So different tools are relevant here like Git, GitHub, GitLab, Bitbucket. So developer writes a code for a restaurant search functionality and then pushes the code to a repository using Git. Then building stage converts the source code into a runnable application. This may include compiling the code, installing all the dependencies, packaging the application, and creating containers. So relevant tools may include Jenkins, Gradle, Maven, Docker. After code is pushed, CI pipeline, that is continuous integration pipeline, start automatically, and your code is compiled and a Docker image is created, for example. So now the application is packaged and ready for testing. Then testing verifies that the software works correctly and has no bugs. It can be unit testing, in which you test individual functions, integration testing that tests interaction between the modules, system testing basically tests the complete application, security testing tries to detect vulnerabilities, and performance testing measures the scalability and speed. So relevant tools in this DevOps stage are Selenium, JUnit, TestNG, and Cypress. So again, mapping to the example that we are considering, a test may check the search functionality. If the test fails, the pipeline stops and the developers then fix the issue. Then release means preparing the tested software for development. Then release means preparing the tested software for deployment. So key activities include version tagging, the documentation, release approval, and packaging for distribution. Relevant tools commonly used for this phase are GitHub releases, the Jenkins, GitLab, CI/CD pipelines. So for example, again mapping to our example, the system may label a release, for example food app v1.0. So the release notes might include added maybe restaurant search, improved login security, and fix maybe the payment bug. Deployment moves the application to a live environment. This can be staging deployment, production deployment. So modern DevOps uses automated deployments. Relevant tools used are Docker, Ansible, Terraform. So again, mapping to example, we deploy the container to the server. So the application becomes accessible to users online. Monitoring tracks the performance and you can say health of your application. It helps detect the server crashes, high response time, security attacks, the memory and CPU usage. Tools used in this category are Prometheus, Grafana, Nagios, and Datadog. So maybe your monitoring dashboard shows 75% maybe CPU usage, response time of maybe 200 milliseconds, and 1000 active users. So if performance drops, alerts are sent to the engineers. Feedback collects insights from monitoring data, user reviews, bug reports, and your performance logs. So this feedback improves the next planning stage. Sources for feedback may include customer reviews, support tickets, analytics, and monitoring reports. For example, users complained search results are very slow. So developers then analyze the log and decide to improve the database indexing, for example, or optimize the search queries. This improvement becomes part of the next planning cycle. So DevOps is not a one-time process, it is a continuous loop of development, testing, deployment, monitoring, and improvement. So software engineering is the principle that transforms the ideas into real digital products used by the millions of people. Understanding its life cycle and domains provide a powerful foundation for building modern software systems. In upcoming videos, we will explore each domain in detail and connect them with modern development practices. So if you want to understand how real software systems are designed and built, stay tuned and follow this series.